Back to looking at a couple of toolkit functions we looked at back the very first couple days of class. And one of them is our friend the reciprocal function. And we know from the work we've done and you've done in the past, the reciprocal function looks like this. Okay, it also has a break here in the graph at the y-axis, and it also has a break in the graph on the x-axis. And so what we've got going on here is we've got what's called a vertical asymptote going on here at x equals 0, and that happens because if I have 1 over 0, remember x is 0 at the origin, 0, 0, and any place along that line, x is 0. And we can't divide by 0, so that's why there's an vertical asymptote there. I'll abbreviate that VA for vertical asymptote. And then as we go out to negative infinity and we go out to positive infinity, this graph's getting closer and closer to the x-axis, because if you think about it, if x is 10 or 100 or 1,000, that's 1 divided by that gets to be a very small number. And if I'm approaching it from the right, or if I'm going to positive infinity, this sustained positive, and a positive divided by a positive is a positive. So down here in my little table I put up, I'm going to put down y approach. Shouldn't be writing infinity. I should be writing 0, shouldn't I? Y approaches 0 as x approaches infinity. And as I approach negative infinity, I'm also closing in on 0 just from the bottom side, from the lower side, so it's still 0. Then as I approach, so that's the ending behavior of this function, right? The ending behavior is the same thing as this horizontal asymptote. Okay, we'll learn some shortcuts here in a minute on how to spot those easily. And so that's the long run behavior. The short run behavior, we're talking about what's happened as x approaches 0. Now these little things that are written as subscripts, that's telling me I'm approaching 0 from the left. Well, if you look at it, I'm sliding towards 0. As x goes towards 0 from the left, y is going down to negative infinity. And as I approach 0 from the right, y is going up to positive infinity. So that's the short run behavior. And we talk about vertical asymptotes typically on short run behavior and horizontal asymptotes for long run behavior. So now we're looking at the second function we'll look at is 1 over x squared. And of course what happens is the x value always gets squared, so we always have a positive value. This also has a horizontal asymptote. As I go out to negative infinity, it's approaching 0. And as I go out to positive infinity, it's also approaching 0. And then as I approach 0 from the left, I see I'm heading up to positive infinity. And as I approach 0 from the right, I'm heading up to positive infinity again. So the vertical asymptote, this one's acting very different than how this one acts. And keep this in mind, that when we have a squared factor in the bottom, it's like reciprocal squared. Or when the graph heads up to positive infinity, it could also head to negative infinity. It'd be acting like, as long as it's doing it the same on both sides, it's acting like 1 over x squared. So here's a couple of functions. We were supposed to find the vertical asymptotes. Well, we can't divide by 0, right? So we don't really care too much about the top at this point. I'm going to factor it just because I can. So x squared minus 4 factors to x plus 2. X minus 2, that's the difference, 2 squares. The denominator is going to factor to x and x. And let's see, to get negative 8, I could do positive 8, negative 1, switch that around. I'm seeing I've got negative 8 in the middle, or negative 7 in the middle. So I'm thinking I want the 8 to be bigger, or the 8 to be negative. So I can't set the denominator equal to 0, right? Well, that's what I'm looking for, and I want to find what's not included in the domain. Well, if I'm solving this quadratic equation in the denominator, x is equal to -1 is a 0, x is equal to +8 is a 0, and those happen to be the places. If I were to substitute those back in, I would get 0 times -9, which is still 0. Can't divide by 0, so that's a vertical asymptote. And the same thing for +8. Substitute that in. 8 minus 8 is 0. I'd get 9 times 0. So that's an issue. Now, one thing I should mention, we don't have 0 on the top, do we? I mean, we have zeros, but when x is -1, that's not 0, and when x is 8, that's also not 0. So what we have is some number over 0 is what gives me a vertical asymptote. This is nice. They've already factored the second one for us, and when x equals -1, that's a place where the denominator is equal to 0, which we can't have. And when x equals +2, that's also isn't in the domain, so we have a vertical asymptote. And in both these numbers, we're going to have a number over 0. Okay? Now this one's got a twist. On the denominator, I'm going to factor that to x plus 3 and x plus 1. So that gives me x plus 3 over x plus 3 times x plus 1. And I hope you're noticing that x plus 3, x plus 3. That's important. Well, let's see. Where's the denominator equal to 0? Well, x can't equal -3. X also can't equal -1. So we think our vertical asymptotes are x equals -1 and x equals -3. And remember what I said about having a number over 0, and that's when my vertical asymptotes occur? Well, if I drop in -1, that's going to give me 2 over 2 times 0, and so that would be a number over 0. That would be what? 2 over 0, and that's a vertical asymptote, so that's one of our vertical asymptotes. But here's where it gets interesting. What happens when I drop in -3? That gives me 0 in the numerator, and I also get 0 in the denominator. Notice that's not 2 over 0 or a number over 0. So this is a different situation. In calculus, you're going to learn a name for this. For today and for now, we're just going to worry about when we have 0 over 0, that tells me there's a hole in the graph. And one way you can tell that without doing too much work is if you look at the factors, if they have a common factor. See how this both had a x plus 3? Well, because that common factor, I know there's a hole. Those could just cancel out, and that would be left with 1 over x plus 1. And we'll talk about graphing that in a bit. I'm going to take a look at some of that work we've done before this video. I could use synthetic division, I could use long division on this. I'm going to choose to use long division because it's not a linear factor down here. So I ask myself, what times x squared is x cubed? That's x. So then I multiply x times x squared is x cubed. X times -6 is -6x. I change my signs. That leaves me 3x. I can't multiply x squared by anything to make it be 3x without going to some kind of fractional, some kind of rational expression. So this equation can become, this function become x plus 3x over x squared minus 6. So what this did for me is this told me that this is the ending behavior, if you remember that work we did. So that this is going to act like, in the long run, this is going to act like the line y equals x. It's just got some crazy stuff happening in the middle here, vertical asymptotes, in a couple of different places, and it's got some twists going on in the middle. So that doesn't have a horizontal asymptote. That has a slant asymptote. And the shortcut way to know that is, this is what we call a top-heavy function. It's got the degree of the numerator is bigger than the degree of the denominator. So because it's top heavy, there's going to be no horizontal asymptote there. So we don't have to go through this whole task if we can just remember that. So keeping that in mind, let's take a look at this. Though the biggest power is the degree of the numerator is 3 and the degree of the denominator is also 3. So if I rewrite this into 3x cubed minus 4x plus 5 over negative 2x cubed plus 6, what we can keep in mind is, sure, you could do the division if you wanted to, but as x goes out to infinity, because that's what we care about, or negative infinity, the 5 and the 6 aren't going to matter so much if you're way out at 1,000,000, right? And the same thing with that 4x. That 4x isn't going to really matter too much because it's getting cubed. But so we can really just kind of ignore all of those and just concentrate on the largest powers, the leading coefficients, the leading terms of the rational function. And then if you think about how those can just cancel off, what we're left with is negative 3/2. So the horizontal asymptote there is negative 3/2. So if you have the same power in the top, same power in the bottom, all you got to do is look at the leading coefficients for each of those terms, and that will be your horizontal asymptote. Now if I'm looking at this one, and so the degree of the top is 1. If I expand this out on the bottom, aren't I going to get an x squared? So this is going to be a bottom-heavy function. As x gets really big, this becomes 1 over a big number. That goes to 0. So the horizontal asymptote is y equals 0. Okay, so if it's top-heavy, no horizontal asymptote. If it's the same power, you look at the coefficients of the leading terms. That's your horizontal asymptote. If it's a bottom-heavy function, the horizontal asymptote is 0. Alright, so this one they want us to find the intercepts and the asymptotes. Well, if I were to expand both of these, I would get 2x squared over x squared with some other terms, but we know that as x goes out to positive infinity and x goes out to negative infinity, those don't matter as much. So what I'm seeing is same power kind of rational function. So we could just think about those crossing off. That would give me a horizontal asymptote of y equals 2. Now to get the vertical asymptotes, well, we're going to look at the denominator, set it equal to 0. Say, where is it equal to 0? Where will x equals negative 2 and where x equals negative 3, because that's those two places that turn those to zeros. And we also aren't seeing any common factors in the top and the bottom, so I know there aren't any holes in this graph. So now we got to find the x and y intercepts. Well, any place we have a y-intercept, x is going to be 0. So if I just substitute in 0 into every place we see an x in this equation, that's going to give me negative 3 times negative 1 over positive 2 times positive 3. And, well, let's see, we could do a bunch of things. I could multiply it at 3 over 6, which reduces to 1 over 2. We could do some canceling. But anyway, that's the vertical asymptote. I mean the vertical intercept, the y-intercept. And then to get the x-intercepts, now it's when we're going to look at the numerator. So ask yourself, where does 2x minus 3 equal 0? Well, that's at positive 3 over 2. And, of course, we know y equals 0. And the other x-intercept, or horizontal intercept, is going to be when x equals positive 1. So 1, 0. And that's how you tackle that kind of problem. So, a couple things I can do to graph this equation. I can ask myself, what are the x-intercepts? Well, I know it crosses the x-axis at positive 2. I also know it crosses the x-axis at negative 4. So I know this graph crosses through these points. I also know there's a vertical asymptote happening at x equals -1. I also am seeing that this function has the same power, and the coefficient is so it's going to be x squared over x squared, and so y equals 1 will be the horizontal asymptote. What else can I find out? About the y-intercept. When x equals 0, y equals -8. So I guess I can start to graph this. 2, 3, 4. 1, 2. 1, 2, 3, 4, 5, 6, 7, 8. I know it's got a horizontal asymptote of y equals 1. It's got a vertical asymptote of y equals -1. And I'll often do this, is I'll draw dotted lines at these asymptotes. Well, here's what I'm seeing. The other thing I haven't talked about yet is this denominator. See how that's like 1 over x squared, except it's been shifted left 1. So that tells me the graph is either going to be approaching up to positive infinity like that, or down in negative infinity like that. And I'm seeing this going on this side. So that tells me it's going to look like this on the other side. So I'm pretty sure that's what this graph looks like without too much more work. Okay, so I hope that process of how I incorporated all this x squared thing tends to give people a hard time. So if they give you the equation, take a look for that, and that'll tell you whether it's acting like x squared or x, just 1 over x. So what are some things I can do with this graph? I know that it's a vertical asymptote at x equals 1. I know there's zeros of -2 and -1, 0, and I also know from our work with polynomials that this has multiplicity too. So it's going to bounce off the graph however it looks. Let's see, it's going to have a y-intercept of 2 over -1, which will be -2, right? Because 2 plus 0, that's 1, and that's going to be -1. Let's see, I see this asymptote, this vertical asymptote, is going to act like 1 over x, not like 1 over x squared. So let's think about, the other thing, the ending behavior is of this function. I'm seeing this would be an x cubed over an x plus 1, so that would leave me like an x squared. So I know the ending behavior is going to look something like this, or something like this. Okay, we don't know which way that's going yet. So now let's start plotting some points. It's going to pass through 0, -2. It's going to pass through -2, 0. It's also going to pass through -1, 0. Let's see. I know it's got a vertical asymptote at -1. That positive one, I mean. I also know that the ending behavior has to look like this. So let's try to connect all this and put this together. So I know this graph's going to come down and pass through that. It's going to turn around and bounce off that graph, that point, and then it's got to head down to -infinity. And we could double check that part of it. As x approaches 1 from the left, let's see, that's positive and that's positive, but like if it's 1/2, that'll be negative, so it is headed down towards -infinity. And then as we approach 1 from the right, everything's positive, so this should head up like this. Now I know this graph on this side doesn't come down as far as the x-axis, because this didn't have a 0 on that side. It only had them over here. So this is a very rough sketch what this looks like. But I do know it looks similar to that. Something a little different. They're asking us to come up with this from the graph again. And I'm seeing two vertical asymptotes, one at -1 and one at +2. So that tells me in my denominator, I'm going to have an x plus 1. Remember, we would change the sign to get the factors, x minus 2. I also know that these both don't act, these both should be acting like 1 over x, because as I'm approaching from the left, it's headed to negative infinity. As I'm approaching from the right, it's a positive infinity, and then the reverse happens here. But still, it's not like the reciprocal squared function. I'm seeing a 0 of +3, so x minus 3 has to be on top. I'm also seeing another 0 of -4, so x plus 4. I'm seeing that perhaps it has a horizontal asymptote of y equals 1, in which case, for what I have written right here, that would give me a 1x squared over 1x squared, which becomes y equals 1. It has a y-intercept of 3, 0, 3. So if I insert 0 into all this, do I get 3? That's the question I could ask myself. That's 4 times -3 is -12 over -2, which is +6. Well, I've got to get that cut in half somehow. So maybe what I should do is I should think about some kind of stretch factor. So I know that it crosses, let's see. When x equals 0, y equals 3. So I can use that fact to come up with my stretch factor. So let's see, so that's a -12 over -2, which becomes 6. If I divide by 6, I get a stretch factor of 1/2, and that kind of checks. If I had split that in half, I would have gotten my 3. So this should be 1 over 2, and that should be the graph, the equation that represents this graph. So I'm seeing a vertical asymptote at probably, I guess, -3. I'm seeing another one at, I'm guessing, +3. So x plus 3, x minus 3. I'm seeing a double root at +2. I'm seeing a single root at x minus 1. X equals -1. I'm also seeing that both of these functions, both of these vertical asymptotes are acting like the reciprocal functions. So if I square this and square this, I'll get that behavior. I guess the only thing I haven't used is I haven't used that y-intercept as 0, 1. So if 1 equals a times 1 times 4, because -2 squared is 4, all over 3 squared is 9, and there's 2 of them. So that would be 1 equals a times 4 over 81, where we're going to multiply by the reciprocal of 81 over 4. 81 over 4, and I'm multiplying, so that a should be 81 over 4. So I am seeing a graph that has a slant asymptote, not a horizontal asymptote. I'm also seeing a graph with a vertical asymptote at x equals 1. It's acting like 1 over x because it's heading in opposite directions. I'm seeing a graph with a 0 at positive 2. I'm seeing a graph with a 0 at negative 1, so I'm negative 3, so x plus 3 and x minus 2. Well, that gives me a top-heavy function, and if I FOIL that all out, that would give me an x squared over an x. It's close. The only thing I must be missing is some kind of stretch factor. So I'm seeing when x equals 0, y equals negative 2. So that's 3 times negative 2 over negative 1, which is negative 2 equals 6a. A equals negative 1 over 3. So instead of a, I'll write negative 1 over 3. And that should be the graph of that function, or the equation this is the graph of.